Okay, so I just wanted to run through some of these that we didn't get to. Um, these two are very similar to the ones we've already done. You just want to isolate x and then graph this on the number line and also show your solution set in set notation. So here you would want to multiply through by 6 so you can get rid of all those fractions. And so you're going to have 2 times x plus 1 because the 3 cancels. Now the 6 is going to cancel. And so you're left with 2x minus 4, and then the 2 is going to cancel with the 6, and you have 3x, negative 3x. And now you want to use the distributive property, so you've got 2x plus 2 minus 2x plus 4, and that's less than or equal to negative 3x. And now you want to get all the x's on one side and all of the constants on the other side. So on the left here, you're going to have 6, and on the right, you're going to have negative 3x. And so you're going to have to divide through by negative 3, which means you'll have to flip that sign to point the other way, and you will end up with negative 2 is greater than or equal to x. And really, the way you would want to write that would be x is less than or equal to negative 2. And that's the set notation. You can put x as a real number on the left side of the vertical line, but you don't have to since everything we're doing right now is real numbers, so, or pretty much. So you can just write your set notation like this, where you put x such that x is less than or equal to negative 2. And then to write it in interval notation, you're just going to go from negative infinity all the way up to negative 2, and you're going to include negative 2, so you use that square bracket, and then you're going to do the same thing for the number line. You're going to put a square bracket on negative 2 and then just point all the way down to the left. And on the next one, this one has decimals, and you can multiply through by something to make those decimals be whole numbers if you want to, but you don't have to. So you can multiply through, do the distributive property, and get x by itself. And so you're going to have your constants on the left and your x values on the right, and then you're going to combine them and divide through by 0.2 once you finish that. So you'll end up with 9 is less than x, which means that x is greater than 9. So you will write that in set notation. You'll just write x such that x is greater than 9. And then for your interval notation, you'll just put from 9 to infinity, not including 9. And then on your number line, you will put a round, a parenthesis on 9, and then have the arrow point to the right. Okay, so on these, you've got 2 different inequality statements, and you are supposed to, the word or, if you have an or between your 2 inequalities, what it means is that you want the first one, you want to graph all the values of x where either the first one or the second one are true. It doesn't matter if they're both true. You just want any number that would work in one of those inequalities. So this is called a union. It gives you 2 different inequalities. So for this first one, you're going to solve for x in both inequalities. So you're going to have x is less than or equal to 7 for that first one. And then you have or x is greater than, if you multiply by 2, you get 12. So you've got 2 statements, x is less than or equal to 7 or x is greater than 12. And obviously, there's no way for any number to be both. So you're just going to graph all the numbers that would work in either inequality. So you're going to graph all the numbers that are less than or equal to 7 and also the numbers that are greater than 12. So you're going to have your set notation x such that x is less than or equal to 7 or x is greater than 12. And then for your interval notation, you're going to start at negative infinity, and you're going to go all the way up to 7, including 7. And then we'll just go ahead and graph that. So you're going to have from 7 down. And then for the other one, you've got x greater than 12. So you're going to say union, because you want to include both of these sets in your solution, union x greater than 12. So that's 12 to infinity, not including 12. And then you're going to graph that as a number line, on the number line. Okay, so the next one has 1/4 y is less than negative 1, or 3 plus y is greater than or equal to 5. So again, you're going to isolate y. So you'll have y is less than negative 4 right there. And then you'll have or y is greater than or equal to 2. All right, so you're looking for all the numbers. Y is less than -4 or greater than or equal to 2. Y such that y is less than -4 or y is greater than or equal to 2. So for your interval notation, you are going to put all the numbers that are less than -4. So that's negative infinity up to -4, but not including -4. And you're going to union that with the other set. But first of all, let's go ahead and graph that. So -4 down to infinity, not including -4. And then you have for your other intervals is going to be from 2, including 2, up to infinity. And then you're going to graph that. Now we have some inequalities where you have an and between the two inequalities. And when you have that and, it's talking about an intersection, which means that both of those, you only want to graph the values that fit in both inequalities at the same time. So -1, 4, t is less than 2. So you want to isolate t. So you would multiply both sides by 4. And you would have -t is less than 8. And then you want to multiply by -1 and switch the sign. So you'd have t is greater than -8. And if we wanted to graph that on the number line, we would just put a parenthesis on -8, and then it would go up. Now, for the other inequality, we've got 0.52, t is greater than or equal to 1.3. So we're just going to divide both sides by 0.52. And when we do that, we get t is greater than or equal to 2.5. So we can graph that by putting a square bracket on 2.5 and going up. So you want to find where both of the inequalities could be satisfied by the numbers in the set that you're going to express. So you can see that there's the blue line and there's the red line. The place where you have numbers that are in both sets is going to be from 2.5 and up. During that period, in that interval, you have both the red line and the blue line, so you know that the numbers will work in both inequalities. So that's the one that represents the intersection of the two inequalities, and so that's the one that you'll put on your number line. Then to write your set notation, you're going to say x such that x is greater than or equal to 2.5, and so that interval, that set in interval notation is just going to be from 2.5, including 2.5, up to infinity. And then for this next one, you're going to solve for w by dividing by 0.36. So w is less than or equal to 1.5. And then on the right, you've got -1/2. W is greater than 3. So you can multiply by 2 or -2. And you would have to switch the sign. So w is less than -6. So you're looking for all the numbers where the numbers are less than or equal to 1.5 and less than -6. Those two sets intersect from -6 down, not including -6. So those are intersections. Okay. Sometimes compound inequality joined by the word and is written as a three-part inequality. For example, if you have 5 is less than -2x plus 7 and -2x plus 7 is less than or equal to 11, you can just write that without the and, putting that -2x plus 7 in the middle. So to solve this one, you're going to start by subtracting 7 on all three sides. So you're going to have -2 is less than -2x is less than or equal to 4. And now you can divide all three sides by -2. And you're going to have 1 is greater than x, which is greater than or equal to -2. So you have to flip those signs when you divide through by -2. And so now you are going to write this in set notation, which looks pretty much just like it does, except that you use curly brackets and you say x such that x is between 1 and -2, which is what you're basically saying, that 1 is greater than x and x is greater than or equal to -2. And so to write this in interval notation, you're just going to show that you mean the set that goes from -2, including -2, up to 1, but not including 1. And then you would graph it by putting a square bracket on -2 and drawing a line up to 1 and using a parenthesis around the 1. For any real number k greater than 0, the absolute value of u is less than k, means that u is between -k and k. So when we say the absolute value of a number is less than some positive number, we mean that the number is closer to 0 than whatever that is. Their absolute value is less than this number k, so they are closer to 0 than k units away. And then if you have the absolute value is greater than k, that means that u is either less than negative k, so it's either k away or greater on the left side or on the right side of 0. So for absolute value of u is greater than k, we're going to have two sets that do not join. They're two separate sets. One where u is greater than k, meaning that it is further away from 0 than k. And then also u is less than negative k because it's further away on the left side from k, away from 0. All right, so we have 2 times the absolute value of 6 minus m minus 3 is less than 7. First of all, got to isolate the absolute value. So you're going to add 3 to both sides, and you'll have 2 times the absolute value of 6 minus m is less than 10. So then you're going to divide through by 2, and you'll have the absolute value of 6 minus m is less than 5. If the absolute value of something is less than 5, it means that that thing, whatever it is closer to 0 than 5 steps away. So it never gets beyond 5 steps away from 0. So we need to write 2 equations. 6 minus m is less than 5, but in order to keep it from going too far away from 0, we have to stop it on the left side of 0. So we're going to say, and 6 minus m has to be greater than negative 5 in order to keep it in that little group right around 0. So negative m is less than negative 1, and if you multiply by negative 1, you will get m is greater than 1, and negative m is greater than negative 11, so m is less than 11. So you have this group of values greater than 1 but less than 11, and that's an and. You're talking about numbers that fit in both categories. And so you've got 1 to 11, not including 1 or 11. And you can also write the set notation x such that x is between 1 and 11. 1 is less than x is less than 11. And then you can draw the number line. Okay, for this next problem, you have to isolate the absolute value. So first of all, you're going to subtract 2 on both sides. And then you are going to divide both sides by 3, and you will have the absolute value of 5 minus x is less than or equal to 4. And that means that that absolute value, the stuff inside of it, has to be closer to 0 than 4. It can be 4 away, but that's as far as it can go. So we have to write 2 inequalities. 5 minus x is less than or equal to 4, and it also has to be greater than or equal to negative 4. We don't want it to get any further away from 0 than 4 steps. And so now we can solve for x. We've got negative x is less than or equal to negative 1. And then for the inequality on the right, we've got negative x is greater than or equal to negative 9. And then when we multiply through by negative 1, on both of these, we have to flip the sign. And so this is what we have. We have numbers that are greater than or equal to 1 and less than or equal to 9. And then your greater than absolute value inequalities, as I said, are going to be 2 disjoint sets, 2 sets that don't share any of the same members. So in this first one, we are going to isolate the absolute value by first dividing both sides by negative 2. And we have to flip the sign when we do that. So we're going to have 2 is less than or equal to the absolute value of 3x plus 1. And since we have actually a greater than absolute value here, because you just need to switch it around so that the absolute value is on the left side, and so the absolute value of 3x plus 1 is greater than or equal to 2. That means the same thing as that first inequality, but this is how we want to write it so that we can write our 2 equation or inequalities. So if the absolute value of 3x plus 1 is greater than or equal to 2, that means it is at least 2 away from 0. So 2 and greater. So we're going to say that 3x plus 1 is greater than or equal to 2, or it can be less than or equal to negative 2. All right, so now we just solve for x. So we're talking about 2 sets. One set is x less than or equal to negative 1. One set is x greater than or equal to 1/3. And so you have to write two interval notations. First one goes from negative infinity up to -1, including -1, and then you have a union of all the numbers greater than or equal to 1/3, so 1/3 up to infinity. Then you have your set notation, you can see it there. And then for your number line, you're going to have two arrows. Okay, these problems are special circumstances where you don't really have to try to solve it because you can already see what's going on. So in this first one, you've got absolute value of x plus 2 is less than -4. Well, you should be able to see immediately that that is the empty set because the absolute value of a number is positive. And this is saying, when is this absolute value, which is positive, less than -4? And the answer is never. You can't have an absolute value that is less than a negative number. All right, the second one, you've got the absolute value of x plus 2 is greater than or equal to -4. Again, this is fairly obvious. An absolute value is always positive, so it's always greater than -4, in which case x could be anything. X can be any real number. And so we would say x such that x is a real number, and then we would also write the interval notation negative infinity to infinity. And then on the far right, you have the absolute value of x minus 5 is less than or equal to 0. It can only be equal to 0. It can never be less than 0 because an absolute value is always either 0 or positive. So there's one place where that actually works, and that's only when x is equal to 5. When x is 5, that absolute value is equal to 0, but it's never less than 0. So the solution set for that would just be 5, x such that x equals 5, and you would just put 5 in square brackets. The absolute value of x minus 5 is greater than 0. Now, that is always going to be true except where x is 5 and the absolute value actually equals 0. This doesn't allow it to equal 0. It's saying, tell me all the x's where this absolute value is greater than 0. So you want to write the set that shows all the values of x except 5. So that would be all x such that x is less than 5 or greater than 5. So that is how you would write the set that doesn't include 5. Actually, most of the time, you would just write all x such that x is not equal to 5. The interval notation is going to be negative infinity up to 5, union 5 to infinity. That's the only way to really do that in interval notation. You're just showing that you're not including 5. Shanice has test scores of 96, 84, 80, 98, and 88. Her score for online homework is 100 and is weighted as 1 test grade. Shanice still needs to take the final exam, which counts as 2 test grades. What score does she need on the final exam to have an average of at least 90? This is the minimum average to earn an A in the class. So she's trying to figure out what she can make that will give her at least a 90. So the way we're going to see that is that she needs to add up her average. So she's got all these test scores plus her final exam. We're going to count the final exam twice. So you need to add up all those numbers and divide by how many numbers there are. And that's 546 plus 2x divided by 8 scores in all. So that is the average. That's the average she will get in the class. So the question is, when is that number greater than or equal to 90? She wants her average to be at least 90. Here we have another application. Suppose that a machine is calibrated to dispense 8 fluid ounces of orange juice into a plastic bottle with a measurement error of no more than 0.05 fluid ounces. Let X represent the actual amount of orange juice poured into the bottle. So the point is that, yes, it's supposed to pour in 8 fluid ounces in each bottle, but it's, sometimes it's a little more, sometimes it's a little less. It's not a perfect machine. So the error is 0.05 fluid ounces. It might be 0.05 more, or it might be 0.05 less than 8 total. So first of all, it says write an absolute value inequality that represents an interval in which to estimate x. So you have the absolute value of x minus 8 needs to be less than or equal to 0.05. So what that's saying is the difference between 8 fluid ounces and what actually gets poured into that bottle, because that's what X is, has to be less than or equal to 0.05. It could be 0.05 ounces less than 8 or more than 8. All right, for part B, it says solve the inequality. So we just need to write the two inequalities that are expressed by this. So if the absolute value of x minus 8 is less than or equal to 0.05, that means that x minus 8 is less than or equal to 0.05. And it also has to be greater than negative 0.05, because we don't want to get it any further away from 0 than that. And then if you solve for x, we have x is less than or equal to 8.05 and x is greater than or equal to 7.95. And so x is between 7.95 and 8.05. When they tell you that each bottle has 8 fluid ounces of it in it with a measurement of error of no more than 0.05, what they mean is at the most, it'll have 8.05. At the least, it'll have 7.95. It's that close to 8. It's very close to 8, no further away than 0.05 ounces.